Welcome back to the main stage. Up next we have the CTO from Fairgate, Sergio Lerner, presenting his talk, Building Secure and Watchtower Efficient Bitcoin Payment Channels with BitVMX. Please give a very warm welcome to Sergio Lerner. Thank you very much.
Working? Okay, great. Thanks for having me here in this conference. Okay, so I'm Sergio. I'm the CTO of Fairgate. I'm also the co-creator of the Rootstock Bitcoin sidechain, the first Bitcoin sidechain. I've been a long time here in the Bitcoin community. Today, I'm going to talk about payment channels, which is not my daily topic that I work on, but it's very similar to the technologies that I'm working on. So I may not use the Lightning Network language that you use, but basically it's the same ideas expressed differently, okay? And since I'm working on BitVM and BitVMX type of protocols that are also fraud-proof protocols, you will see that I'm bringing a fresh look, a new look into the payment channel problem in Bitcoin. So the agenda for today, first, I'm going to briefly explain why we need payment channels. Obviously, many of us here knows about this well, but maybe we have newcomers. And then I explain the evolution of payment channels until the Lightning Network payment channel. And to introduce these new types of payment channels, I'm going to introduce one-time signatures on Bitcoin, and then the one-time signature payment channel, which is a completely new construction. Then I'm going to introduce BitVMX very fast, and then I will show you how these one-time signature payment channels can be transformed into a BitVMX-based payment channels. And that's the idea. So why we need payment channels? Because Bitcoin transactions are slow, they take more than 10 minutes, and also we have limited space on the Bitcoin blockchain. And so if we want to do high-frequency payments or everyday DeFi or everyday payments, then obviously we need a layer 2. And so payment channels allows two parties to exchange as many payments as they want, and with the security that they are settling on Bitcoin. So using this fraud-proof mechanism, and as long as the challenge window is long enough so that there cannot be any censorship, we have Bitcoin security. Okay, so we can perform thousands or millions of payments between two parties, and actually settle with one transaction on Bitcoin, and then we can combine payment channels to create a Lightning Network. Okay. So it all started with Nakamoto himself. He proposed an idea to create a payment channel. Basically, Satoshi's idea was incrementing the end sequence field of each transaction and sending that to the memory pool. And kind of he thought that the last of this transaction will be the one picked by the miners, which is obviously very fragile. Miners couldn't pick any of these transactions, so it didn't work in practice. And also, it had a problem of transaction malleability. And then we had these Pillman-style unidirectional payment channels, which solve the problem of mempool. Basically, they are enforced with consensus rules, but yet they are unidirectional, and they have a expiry time, so you can use it until a specific time. So they are obviously have some limitations. And then when we had this check log time verify opcode in Bitcoin, we could create a variant of Pillman channels using this opcode, which eliminates the problem of transaction malleability. Well, then we have the ones that are more in use today. The duplex construction by Decker and Wanterhofer. It's the first bidirectional one, and it uses two unidirectional channels connected with an invalidation tree. And it's good because it's bidirectional, but the problem is that there's a lot of complexity with handling this invalidation tree, and also it has a finite number of updates that you can do because you have to bring forward the expiry time. And we arrived to the channel we use today. This is the Poon Draija, where funds are locked in out of two multi-signature, and it's bidirectional. It uses hash time lock contracts to power the Lightning Network and to connect several of these channels together. but it's very complex. I used to be, I think I used to be a very kind of an expert on this topic 5 years ago, and I am not anymore, which means that information fades very quickly because it's a complex protocol, and you have to be, in a daily basis working with a Lightning Network node to be able to have full knowledge of all these bolt and beeps and everything that is happening there. Well, there was a new design which is called L2, and that has very interesting properties. It provides efficient watchtowers. One of the problems with the previous design is that watchtower had to store a lot of information. So maybe if there's an enterprise watchtower, that's no problem because they can, have a terabyte of space. But if you want to hire more cheap or more decentralized watchtowers, then it becomes a problem. Well, this construction requires a soft fork in Bitcoin, either any prev-out Zcash or no input Zcash, so it's not possible today. And there was a paper, and this one I found just last week, that is called Outpost, that provides a watchtower efficient payment channels. It's kind of a modification of the PON construction. And it's funny because it requires that every state commitment stores the revocation message for the next commitment, encrypted in that commitment. So it works by storing that transaction data on an op return, and it consumes about 300 bytes, which is funny because with these changes on Bitcoin Core, we could enable, for instance, this protocol to work very efficiently. And the only drawback is that it requires, in case of unilateral exit, you have to publish this blob of information on chain, which consumes over 1,000 weight units. But today I'm bringing you two new payment channels designs, which I think are much better what we have in existence now. One is based on one-time signatures, and these one-time signatures became very popular with the BitVM protocol because it was the first protocol who relies heavily on one-time signatures for the input. But this construction is, separate from that, separate from BitVM. It's very simple. I hope you will understand it in just one slide. It's watchtower efficiency and provide watchtower privacy, which is something that none of the other protocols really provide. And the drawback is that in the case of unilateral exit, you need to spend more than 700 weight units, which is not a lot. And in the case of a dispute on the unilateral exit, then another 750 weight units. And then I'm going to show you how you can transform these one-time signature payment channels into a BitVMX power payment channels, which gives you a lot more programmability on the payment channel at a certain cost. So first of all, what are these one-time signatures that I'm talking about? This is a very old cryptographic construction. It dates to, I think, the 80s or the 70s. So basically, it's like public cryptography. You have a public key and a private key. You have a key generation primitive, a signing primitive, and a verification primitive. This is all normal. The only thing here is that you can use only the public and private key once. And if you try to use another time, then you break the security and message signatures can be forked. Okay, so you have to make sure that you use it only once. And the other problem is that you are going to sign bits of information. Like if you take a long message, you will have to sign every single bit or group the message into nibbles or something and sign them separately. So the size of the signature is not constant, but it grows with the number of the size of the message, okay? So I'll give you an example that works on Bitcoin today and you can use for any script. So basically creating a 1-bit Lamport signature is creating two hashes, Q0 and Q1. Obviously you have to first create the pre-images, P0 and P1, and you hash them, you get Q0 and Q1, and you publish Q0 and Q1. That's your public key. And when you want to sign the message, you just reveal one of these pre-images, either P0 or P1. And to verify that, you take the message. If it's 1, then you check that the P that you receive hash is Q1, and if it's a 0, you do the opposite and check it if hash, it gives you Q0. So very simple stuff. And when we implement this on Bitcoin script, you get pretty small program, but remember that this is just to verify a 1-bit signature. Okay, so this is 32 weight units per bit, which means that if I want to sign a 32-bit number, for instance, it takes more than 500 virtual bytes. So it's kind of 3 standard transactions, or maybe 4 standard transactions, just to sign 32 bits. But since we are going to be signing only 32 bits, it's pretty practical. And there are more optimized schemes that we are using in BitVMX and in BitVM. It's Winternitz is one of these schemes. It gets you to 1/3 of this size, so you can use that and optimize it. I'm not going to go into the details here. So what are these one-time signatures-based payment channels? So this is the idea. This is the whole thing. This is the whole graph. Okay. So there are a number of transactions. Most of them you have to sign every time you do a channel update. But essentially, there are 3 of them which set up or commit to the balance at a specific state. These are the start transaction, the assert transaction, and the pay transaction. So basically, in the start transaction, what you will do is the following. Each one of the updates has a precise, a unique sequence number. So in the start transaction, this is the 3 transactions you will build each time you are doing a state update, okay? 3 new transactions every time you want to do a state update. So in the first one, the start transaction, you basically force the assert transaction to sign with your own time signature the sequence number. So in start sub I, basically I force the assert sub I to sign I. So pretty simple. And in the pay transaction sub I, basically I just pay to the 2 payment channel owners according to their balances in that state. Okay? So just forcing you to sign with the one-time signatures the sequence number of your commitment. That's very simple. But then you have 3 or 1 per party transactions that allows the party to revoke any attempt to sign a previous sequence number. So I call them revoke Alice all states and revoke Bob all states. So each time you do a new state commitment, you create a new revoke Alice all state, a new revoke Bob's all state, which has the following logic. If you give me a sequence number J, which is below I, so in the revoke transaction sub I check that I force you to give me a sequence number J signed by the other party, and if you can provide that signature, I just take all the funds. Okay, so the Alice wins and Bob win transactions there, basically they provide the J signed with the sequence with the one-time signatures, and they take the funds. Okay, so this is everything. There are some timeouts involved in the middle, like what if I publish the start transaction and I do not publish the assert transaction? Well, there are some punishment transactions that are the timeout for Bob and timeout for Alice. And I use a secret, a pre-made secret, to decide which of these 2 timeouts is going to be active. So the party who issues the start transaction also has to reveal a secret, PA or PB, which is hashed to 2 known values. And so the one that is provided allows the other to start the timeout. And of course, the other is not a variable. So it's everything. And the good thing is that we can have a different revoke transactions that we can give to the watchtowers. This is the watchtower B, the Bob watchtower revoke Alice all states. And we can tie that to a Bob and watchtower wins transaction that actually split the funds differently. For instance, it can give a part of the funds directly to the watchtower. So the watchtower can have an incentive, direct incentive, to issue that transaction. And then we will see how we can all make this private. Okay, what's the setup? Very simple. First, the 2 parties, each one of them chooses pre-mage, PA, and PB. These are only for the timeouts. Then each one of the parties chooses a secret one-time key and a one-time keeper, the key A and key B public keys, and these are sent to each other party. Then they both create and issue on chain the setup transaction, which is basically a transaction that locks the funds. And they will also create two first versions of the pay, assert and start transaction. The pay 0, assert 0, and start 0, which basically distribute the funds according to the original balance when the payment channel was created, the setup. Okay, and this is done. So let's zoom in and see what happens when we need to do a state update. So state updates are very simple. First, we sign all transactions that I showed you, except for the start and the revoke transactions. Why we can sign them and this has no implication is because they depend on the start and revoke transactions, so nothing wrong can happen if we sign them. When I say sign them, I mean two-party signature, either with multi-signature or music2, so they are protected like covenants, right? It's two parties agree that these are the transactions of the protocol. But then we have to be very careful on the order we sign these other three transactions. So first, what happens is that Bob will sign, I put a circle there with Bob's color. Bob will sign the start transaction. So now Alice has a little bit more power. Alice can decide to unilaterally exit with the state I-1 or the state I, because she has her own, she can sign the start transaction. But since we are modeling here a payment from Alice to Bob, the order I'm giving you is the order that protects both of them. So Alice does not get any advantage for publishing the latest state because he's paying Bob. So the second thing that happens is that Bob signs the revoke Alice old state transaction. So at that point, Alice cannot use the old state because she's by that. Sorry, Alice signs the revoke Alice old state. Then Bob signs the start transaction, and at that time, so Alice, I missed the color, I switched the colors. Alice signed the start transaction, and at that point in time, both of them could use the start transaction, and finally, Bob signs the revoke Bob all states. You can see that there is no middle state where any party has any advantage. And the order is established so that Alice is paying to Bob. Okay. So what happens with the penalization? How does penalization work? So let's say that Alice wants to unilaterally exit with a state that is state J, which is the state number 50, while the current state is the state number 100. So she will publish on chain the start transaction, and then a timer starts, a timeout, so she must issue the assert transaction. And when she signs this value J with the key A, basically she's done because she's going to be punished. Okay, so at that time, Bob comes, takes the latest revoke Alice all state transaction, and this is transaction of state 100. Bob does not need to store any other previous transaction, and publish this on chain, and then with Alice's signature of the value J, he just issue the Bob wins transaction and takes all the funds. Very simple, okay? We can do obviously HTLCs, hash time lock contracts. I think this is even more simple than in Lightning, because there's only two paths per HTLC. There is no relative time locked path. So basically, each one LTLC will be a new output of the pay transaction that we create. And each of these outputs, obviously depending on the order, will have a hash lock spend and an absolute time lock spend, which must obviously reflect the timeout that the two parties set up off chain for that particular payment, right? And so if the pay transaction is issued on chain, then each of the parties can take the HTLCs that correspond to him or that needs to collect, and everything works. Closing the channel is very easy. You have the cooperative close, where basically two parties sign a transaction that just distribute the funds out of the setup transaction, so it's very cheap. And when there is an unilateral close that is not disputed, and then the party issues the start transaction and the assert transaction of the latest state, they wait until the dispute period is over, and they issue the pay transaction, and it's all on chain. So these are only 3 very small transactions. There is no need to, and then obviously if there are any other funds to collect from the HTLCs, they can do it at that time. So what is interesting about this construction, it gives you a lot of possibilities to improve watchtowers, for instance. So first of all, watchtowers only need these 2 transactions for each new state, and they can throw away everything before that. So they only need, in fact, if we are not going to distribute the funds specifically to watchtowers with the Boban watchtower B wins, then you don't even need to give it. But let's suppose you need it. So only 2 transactions is all they need. You could even encrypt this transaction with a secret that is revealed in the commit transaction. In the start transaction, you can create 1 new secret for each commitment, for each start transaction, so that every time you have a unilateral exit, you provide the decryption key so that the watchtower can decrypt it. That gives the watchtower no information about what it's watching for, which is good. And so basically with this construction, you can hide the update rate. This is optional. You could even hide it from the watchtower and do not give the watchtower any channel ID. And the watchtower obviously had to monitor every single start transaction that sees, but you could do it. And the channel ID, you can hide it from the watchtower, and you will also hide the amount for all the updates except for the one that goes on chain, except for the one that is actually disputed on chain. So the watchtower does not know, not even the amounts. So this is good. So a summary of what we've seen until now: there is a new type of payment channel. It requires only constant space, but watchtowers, they need to store very small amount of information, like 2 kilobytes. This means that also the participant needs to store very low amount of information, because the participants are watchtowers themselves. So each participant needs almost no memory at all. There is no need for Bitcoin softforks, because one-time signatures we couldn't do today, even if we could obviously improve it with many of the proposed new opcodes. We have this full watchtower privacy, and we support HTLCs. So if we had 2 parties on the Lightning Network using this protocol between them, then basically they will be 100% compatible with the Lightning Network. But of course, you need both peers on both sides to be using this protocol. So I have very little time. I'm going to explain what is BitVMX and what BitVMX can bring into this. So BitVMX is a virtual CPU that you can verify on Bitcoin using a verification game. It allows you to execute arbitrary numbers of steps of chain, and you only need to perform on chain a number of operations that is in the logarithm of the number of steps you execute off chain. And we are implementing a virtual RISC-V CPU, so it's very standard, and you can program that with Rust or with C++. And the whole thing was invented, BitVM was invented by Robin Linus in 2023. You probably heard about this. The BitVMX platform was created by a joint effort of Roosstock Labs, Fairgate Labs, and then Cardano also participated. And how does this work in a nutshell? So first, the prover will post an authenticated program input on chain in case of dispute. When I say authenticated, I mean OTS signed, because we don't have the opcode checksum from stack, so we have to use one-time signatures. So the verifier takes this input and locally his own computer runs it through the virtual CPU and creates what's called execution trace. I don't know if you are coders and you probably had to debug something at the assembler level, and you see, each one of the opcodes and the outputs. Well, this is the execution trace. This execution trace is converted into a hash chain, which includes each one of the trace items. And then the prover and the verifier engage in a verification game on chain, bisecting this chain, trying to find, the malfunction point. The point where the verifier notes that there is an instruction executed that has a correct output followed by an instruction that is incorrect. Okay, so at that point, they have to decide what to do. So the challenger would probably ask the prover more information about that specific step, which memory addresses it accessed, what I don't know, register it's using, the opcode in particular, and it also happens on chain, and then the challenger will challenge one of these properties. So like either the hash chain is broken, or the memory access is incorrect, or the opcode execution is incorrect. Any of these three things can be a cause to a malfunction. And then the challenger, with this information, goes on chain, and a Bitcoin script. There is one Bitcoin script for each one of the potential opcodes, the rich5 opcodes. We'll take all these arguments that are signed by the other party, the counterparty, and we'll decide where to give the funds to. Okay, so I think it's pretty simple. This is how the hash chain is created. So we use Blake 3, and we have the previous step hash, and we combine it with the trace. We get a new step hash. On chain, what actually happens is a sequence of transactions, very simple transaction graph, where in the first, the prover provide mid states of the computation. We don't do binary search, but a partition of the whole mid state space. So you get a lot of mid state, like 8 mid states, and then the verifier chooses one interval between 2 mid states, and then the prover expands that interval and gives you more mid states until they find the instruction. For instance, this is an example of a binary search, which is not what we actually do, but it shows how you can iterate between a malfunction point, which always the last state is invalid, because if not, you wouldn't be challenging, until you get to a point where you have one correct instruction followed by an incorrect instruction. Okay, so how can we improve payment channels with BTC? First of all, instead of having a specific logic tied to Bitcoin script regarding how to revoke previous state, we can just sign a message that it says, we revoke all state prior I. Okay, that's the message. And we sign it with Schnorr signatures, because we have a program that is able to check Schnorr signatures. So Alice will sign it with the SA, and Bob will sign it with the signature, will produce a signature SB. And this is the protocol. It looks very similar to the one previously. I only added the dispute channels after the revoke transactions. So the revoke transactions are only providing the input to the dispute channels. The dispute channels have all the logic that I told you about, the exchange of messages is all there. And we add to these revoke transactions the signatures of this revoke message. So we could do anything there, like verify BLS signatures or Schnorr signatures, whatever. So the only 3 changes that I made was adding the dispute channels. We need 2 additional one-time keys, because we need to double sign these inputs, like Bob and Alice both need to sign them. So there is a new pair there specifically for that. We cannot reuse the other because they are one time. And we add these 2 signatures, SA and SB, and that's all. We can do the same with the hash time lock contracts, and we can add a dispute channel for each one of them. So basically, instead of using a hash, which has some privacy implications, one of the problems of the existing construction is that when there is a dispute and it all goes on chain, then anyone can trace, connect all the channels and see who paid who, at least in a pseudonymity way, right? And with this, we can hide it. We can do things similar to point-time lock contracts, because we have a full program that evaluates this. For instance, we can use an elliptic curve discrete log hash function. So we can, by multiplying each point with a random factor, we can separate the on-chain transactions and make them completely untraceable. Okay, so this is another benefit. So to summarize, because I'm running out of time, we have a new payment type which is more powerful, also requires constant space from the watchtowers, and it supports more privacy, I would say, and more programmability. This is not the end of the story. The BitVMX platform currently supports one protocol, but we are working on using garbled circuits. We have we are in the middle of a research on using garbled circuits directly on Bitcoin, and so that will reduce the cost of disputes. Currently, to dispute a Schnorr signature, it takes about this is an estimation based on the last time I checked transaction fees, like $80 transaction to a single dispute, which for large payment channels, no problem. But if you are creating very small amount of payment channels, obviously it's not good. But we can lower this to about $16 per dispute using garbled circuits. Okay, so our estimation is that verifying, for instance, a Schnorr signature, it takes 7 million gates, which is completely practical with our current implementation of garbled circuits. And BitVMX started being just the protocol, the CPU, but now it's a lot more, has many different components, and for each one of them there is a paper that has been published. So we have the CPU, we have the garbled circuits implementation that we are in the middle of it. We have the Flex protocol that allows you to put more funds dynamically on demand on any dispute, so that you can hire the bar for that dispute. So dynamically add more funds for a specific dispute. And that allows us to create, for instance, Battle Protocol, which allows to create a committee of 1,000 challengers, and for any one of the provers be able to dispute, to defend an assertion in front of, against 1,000 challengers with a fixed amount of security bond. Does not depend on the number of challengers. That creates, the possibility to create much more decentralized protocols. So I'm reaching the end of the presentation. So to summarize everything, just created and show you 2 new types of payment channels. These are, you could, the OTS one, it's very practical. I mean, you could implement this for a hackathon if you want it. I have not implemented myself, so feel free to create the first implementation of these payment channels. And they support efficiency and private watchtowers, and also support root hiding mechanisms like point-time lock contracts. These are all based on BitVMX ideas. So the source of all this, enlightenment comes from Robin and his ideas with BitVM. But BitVMX is really the only BitVM implementation that currently is robust and cheap and performant. Like BitVM 2 implementation, it only verifies Grok 16 circuits, so it's huge, and it takes like $100K to dispute on chain, compared to a few $100 or less than $100 for BitVMX. So it's completely different thing. You have the garbled circuit implementation of BitVMX coming, and I hope this will be in the upcoming month. And I think we are all just scratching the surface of garbled circuits in Bitcoin. Like, there's so many possibilities. So I expect like new innovation happening in the following month. So expect something new happening soon. Okay, that's all. I'm on time. Thank you very much.
So we are going to be taking a break in a moment, but we will do a question or two before we do, and I thoroughly encourage everyone to participate in the BitVMX challenge in the hackathon over the next 3 hours, when we're taking a break before returning at 6 p.m. for further talks here. Any questions for Sergio?
Okay. Thank you.
I wish you all lots of luck in the hackathon, and thank you very much to Sergio.